Okay, so we're testing, and especially in regard to abrasion. So either there's a pin on abrasive disc or a pin on abrasive plate, pin on abrasive drum, or then a rubber wheel abrasion test. So that's the 4 different things that we can do. So with a rubber wheel abrasion test, you've got a sample here, and you've got sand that comes through at a certain rate. The rate is determined. You've got a weight that you apply, and then your rubber wheel turns at a certain speed. And you do the test. You weigh the sample beforehand, and you also weigh it afterwards, and you do it for a certain amount of time. Or another alternative of this is you've got your sand, and on a slotted drum, then you've got a feed chute which lets the sand go through, some fluid feed, so also to look at the influence of fluid, and then your drum that rotates here with the sample sitting down there. Okay, then we want to look at adhesive wear. Adhesive wear is when 2 bodies slide over each other and fragments are pulled off one surface and adhere to the other. So fragments may later come off the surface and either form loose wear particles or may be transferred back to the original surface. So we've got component A here and also B down there, and we see that B bonds to A and is ripped out of B. So bond B1 is the bond between A and B. Bond B2 is the bond between particles in B. So that's why it's and so B1 is stronger than B2. So B1 will be there, that's B1, and that's B2. So B1 is greater than B2. Corrosive wear, this we've spoken about in the corrosion side. So that's the synergistic interaction between chemical reactions and the wear process occurring simultaneously. And corrosive wear might have higher wear rates than separate wear and corrosion processes. So there's the combination of the two gives you a higher wear rate than either or. And it may have subsurface corrosion while wear proceeds at the surface. And corrosive wear is facilitated by increased temperature, surface roughness, and a dislocation density. Surface fatigue wear, this happens during repeated sliding or rolling over a surface, and the surface is exposed to repeated loading and unloading stresses. It can result in the formation of surface or subsurface cracks. So that would be a surface crack, and a subsurface crack will be here. And cracks may cause breakup of the surface, leaving pits. So we typically see this with gears. So if that is your gear tooth, then you're going to have another gear tooth coming in like this. My gear teeth are not very good, but it's something like this. So as the gears are moving, you're going to get very high compressive stresses, which will also cause shear stresses at the below the contact point, and that's going to give you cracking. So typical conditions under which surface fatigue occur is high normal and shear stresses, variable in time and acting underneath or close to the surface. Existence of subsurface defects. So, of course, this is a fatigue type of mechanism, and so a defect will give that initiation point for the crack to start. So that's in the region of active stresses, mainly due to fabrication processes, maybe through heat treatment or machining, etc. Then fretting. So this is the small oscillatory movement between two solid surfaces. The direction of motion generally tangential, causing material removal in the form of flaked particles. And the motion amplitude lies between 1 and 100, probably micron rather. It can be as low as nanometer amplitudes, or maybe even into the millimeters, but typically it's a very small amplitude. And fretting can lead to either increased clearances or seizure. So seizure being where it sort of welds to one another. And of course, with fretting, we also saw that corrosion plays a significant role. Then erosion. Erosion is an important process that this is where a particle carried in either a fluid or a dry medium hits a solid surface and removes material from it. So for dry conditions, you get solid particle erosion, and wet conditions, slurry erosion. So you get the particles come in at a certain angle and they hit on the surface, and it maybe gets bounced off, or they carry along the surface. So there are two possibilities: low speed corrosion, so grains impact the surface at an angle and move along the surface for a distance, or they bounce off. While moving along the surface, they may cause abrasive or adhesive wear, and the speed of the grains is typically 5 to 200 meters per second. So this is for sandblasting and oil pumps with crude, so pumping crude oil that would contain salt, not sand. So in oils where you've got sand as well. Then high-speed erosion. So the particles hit the surface at high speeds, causing crack initiation and growth, and leads to material removal. So the ductile material wears at a slower rate than brittle materials. That's quite important. So your ductile material is actually better than your brittle. Erosion can also be caused by high-speed water jets where no particles are present. So, and you even get this technique where they do cutting with a water jet. So examples is aircraft bodies and also turbines. Then the type of wear testing for erosion. So either jet impingement, so you've got a gas that comes in at a high rate and it blasts the particles, sand particles, onto a surface. And of course you can rotate this surface. Then we also have a recirculating loop. So this is more of a closed circuit. Over here you get the particles to move in that direction. Or you've got two sand coming in from the top, and you've got this surface just spinning around, or maybe the sand is only on the ends and you spin it like that. So whirling arm rig or centrifugal accelerator. You could also, in terms of the slurry, have maybe your specimen here, you pump your water, measure the flow rate, and that is blasted onto the sample, but it then gets the sand into that, and you measure the erosion of that particle. Then the extent of wear predominantly depends on the number and mass of particles striking the surface, impact velocity, and impact angle. So it's the mass of your particles, the impact velocity, so how fast they come, and at what angle they come. So E, your extent of wear, is equal to the mass of material removed divided by the mass of erosive particles striking the surface, where E is equal to K, the wear coefficient, times then the density of the material being eroded, times the impact velocity squared divided by 2 times the hardness. So we see that erosion, we get these two behavior, linear erosion, where there's no incubation behavior, or B, where you do have an incubation stage. So this is the mass of the abrasive that you apply. The loss is like this. So linear erosion, just initially from the beginning, there's a loss in material. But with non-linear erosion, you first get a period where there's a bit of gain, and then the erosion continues. So we see for copper how erosion, the milligram per gram, how that relates to your impact velocity. So we see that as the impact velocity increases, you're going to have a higher erosion rate, but it also depends on the impact angle. Then if we look at hardness, so erosion as a result of the hardness, so we see that as the hardness increases, there's of course a decrease in the erosion of your material. So also look at the annealed hardness. It's a little bit low, but it's quite similar in your erosion. It's very on the same, slightly lower erosion of the hardness after erosion. Okay, so the effect of the impact angle on the erosion of ductile versus brittle materials is depicted in figure 26. And so in general, impact angles are defined relative to the plane of the surface being struck where normal impact occurs at a 90-degree angle. And the combined effect of particle size and impact angle on the erosion of soda lime glass is shown in 27. So let's see. Here is the effect of the impact angle. And we've got erosion on the Y. So we see for ductile materials, the impact angle, a little bit less than 20 degrees is where you get the maximum. Where for brittle materials, your impact angle is the worst at 90 degrees. For ductile materials at 90 degrees, it's a little bit less than, it's quite a bit less than at 20 degrees. And so here we see the effect of the particle size. So when the particle size is small, then the impact angle reaches a maximum just below 30 degrees, but when you have larger particles, then your impact angle is probably almost the highest at 90 degrees. Then cavitation erosion. So this is the growth and implosion or collapse of gas or water bubbles on a surface within a liquid subjected to rapid and intense pressure changes. When the bubble bursts, the jet of liquid from the top of the bubble travels at speeds of up to 20 to 100 meters per second and impacts the surface, causing erosive type surface damage. And cavitation is frequent on high-speed propeller blades and is one of the major causes of pumping problems. So we looked at this. So when your pump is cavitating, in addition to not pumping the liquid at optimum efficiency, the pump may also be subjected to internal damage, seal and casing leakage, bearing failure, etc. Then thermal wear is the removal of material due to softening, melting, or evaporation during sliding or rolling. So this is where you've got maybe thermal shock or high temperature erosion and wear by diffusion of atoms from one body to another at high temperature. So remember, at high temperatures you get a lot of other mechanisms that also take place. So how do we limit wear in the design process? Is first we need to establish if significant wear will take place. Then we need to take steps to reduce the wear rate with the economic and other constraints of the design. And then changes which we can do is the change of your component, remove sharp bends from pipelines, for instance, or change the operating variables, maybe reduce the load or the sliding velocity. And then lastly, of course, it's very important, the change in the material. And that's where surface engineering comes in. So first of all, you want to improve wear resistance, and you also want to modify frictional behavior. So surface engineering processes, you do first of all surface modifications or add surface coatings. Surface modifications are two things. So first of all, microstructural modifications or compositional modification. So microstructurally, you can do flame hardening because, of course, hardening is going to improve it. Flame hardening, induction hardening, or laser hardening. We also get laser shock peening, and with that you induce a compressive stress. Or compositional modifications, carburizing, nitriding, anodizing, boriding. So all kinds of things that you can do to the surface. And then the second big category is surface coatings. Maybe a weld cladding, so fusion hard facing, or a thermal spray that you add, or electro-deposited coatings, or electroless deposited coatings, or vapor processes. So lots of different surface coatings that you can apply. Then microstructural modification, generally used for ferrous alloys, so suitable phase transformation. So, for example, pearlitic steel is heated to the austenite and then quenched to form martensite. But you do that on the surface generally so that you form a very hard surface. This gives short process times and is useful for small areas. So gear teeth are one of these really very useful things. Alloy must be hardenable, so you have to have a steel of maybe more than 0.4% carbon, plus alloying elements like chromium, nickel, and molybdenum are very useful. Compositional modification, this is where you've got your solid state process, by which atoms are transported via the thermally enhanced diffusion into your surface layer. So two types: interstitial solid solutions. Small atoms are diffused into the substrate layer, and they form compounds as fine precipitates. And then you also have regions remain chemically similar to the bulk. So this, for instance, carburizing. Chemical reactions is where you form a new compound at the surface due to your chemical reaction between diffusing atoms in the substrate. So this is nitriding, boronizing, chromizing. And the interface layer has high strength. Coating processes. This is where the layer of material deposited on the substrate surface, and the coating thickness varies from microns to millimeters depending on your application.